Hello everyone. My name is Byron Gaspard, and this is the final presentation for RoboBoat. We're team B04, and I'm joined by my other teammates, Sammy, Justin, Zhao, and Jai Singh. And so a little outline of what we're going to cover today. We're going to start with the project background, talk about some proposed solutions, how we have tested them, the planning that was involved in the project, and then at the end of it, we'll do a demo. And so RoboBoat is an annual student competition held in Florida, and it has two primary goals. The first of which is as an educational tool to encourage engineering, innovation, and interest in the autonomous surface vehicles. And the second is to develop affordable autonomous surface vehicles that can navigate courses to mimic situations that a typical commercial vessel would encounter on a regular basis. And so the project has been at Temple since 2014, but has only been to competition once, which was in 2016, and has never returned. And so we determined that the primary reason that Temple has not returned is that the previous teams did not design with the consideration of how future teams would be able to pick up and iterate upon their work. And so our team's goal is similar to the competition's goals in the long term, but it's different in the short term. And so our goal is to develop the boat's core mechanical and software infrastructure. That's our primary goal. And in the long term, this will provide a stable base from which future teams can iterate upon and implement that autonomous functionality required for the competition. And so 90% of the world trades is carried by sea at some point, and reliability of this shipping network is critical, and its failure would leave millions without essential products. So fortunately, between 75 and 96% of maritime accidents are caused by human error, and automating shipping vessels would largely decrease these accidents and increase the reliability of the global shipping infrastructure, therefore reducing collisions. And so this shows how it's aligned with the UN's Industry, Innovation, and Infrastructure Sustainable Development Goal. Fuel consumption and carbon emissions could also be reduced with autonomous surface vehicles by optimizing path plan to minimize the fuel expenditure. And so with these considerations, the automation of vessels is clearly an important engineering problem that should be addressed. And so our functional requirements for this project were designed from were pulled from two places, either the competition's core requirements or pain points that we recognize after starting work on the project. And so for the competition side of things, the boat needs to be remote controllable, so it can be driven from dock to a specific course during competition. An emergency system also needs to be implemented that can be used to safely stop the boat by cutting power to the motors. And part of that system is the status indicator lights, which indicate the operational status of the boat, whether it's stopped and safe to approach, whether it's being manually piloted, or whether it's autonomously piloted. Sensitive components and dangerous components also need to be labeled to prevent the sensitive ones from becoming damaged and to prevent the dangerous ones from hurting competition staff or other participants. And all components need to be water resistant, as it's a rain or shine event, and the boat also needs to be positively buoyant, which might be obvious. But the self-imposed requirements that we selected, the first of which is that we need to have an expandable power distribution system and monitoring system to protect the boat's operators and equipment, while also making it easy to add new components to the boat by our team and by future teams. Second, we needed to make sure that our solutions that we plan and we believe will be kept for the long term are actually implemented and built so that they will hold up. And so an example of this is using fiberglass to seal the hole instead of silicone caulk, which is what previous teams have done. Third, the systems that do need to be subject to change need to be easily able to change without drastic redesign, so it needs to be modular. We also need to implement a single source of truth for all sensor and control data. So all this can be aggregated in a single location and accessible for processing when a machine model or when a machine learning model is going to be trained. And lastly, we need thorough documentation and version control to allow for future teams to easily restore everything to a known working condition should they break it when they try to add some new functionality. And so the first portion of this we're going to discuss is the power distribution system. It was designed with three considerations. The first safety consideration for it, we determined that all electrical connections needed to be current limited to mitigate the risk of shorting out a battery. Additionally, a relay for each motor capable of breaking the 16-volt, 25-amp max load needed to be selected and installed. For the simplicity portion of it, we recognized early on that one pain point would be transitioning between in-water testing and in-lab development, as all the components would need to be removed when in the lab and plugged into the wall power and monitors. And so to simplify this, we added shore power to the boat so that when you move back into the lab, the boat can stay as assembled and as it is, and you just need to plug in an external power supply, which is a modified Xbox power supply, and use a power changeover switch that you can see labeled on the screen to select between shore and battery. We also wanted to make sure it was upgradable. So this is two parts. The first was selecting components that were overrated for what they were going to be doing. So the relays, for example, are able to handle up to 30 volts at 30 amps, and we're only putting in 16 volts at 25 amps right now. So there's room in that. And also you can see on the fused connections that we have, there are open spaces where new components could be added to the system with relative ease and without having to do anything too drastic, as these are all connected through crimped screw terminals. And so it's relatively easy to add new components onto that. To support the power distribution system, we also needed to develop a system that monitors the health of the batteries. The boat is configured to use 3 LiPo batteries. And these batteries can become irreversibly damaged if they are overcharged or over discharged, or if one of the cell becomes unbalanced. And the unbalancing can occur if a battery is under a high load for an extended period of time. All 3 of these faults can result in a catastrophic failure mode of thermal runaway, which is when a battery essentially will flame out and could even explode. And so we want to be able to detect all of these things, and so we can respond to them in real time, as opposed to finding out with a smoking boat as our indicator. And so the monitor circuit uses voltage dividers to step down each of the cell voltages, so that could be measured with one of the Mega 2560's 16 ADC channels. And each measurement involves averaging 100 ADC readings per pin, scaling those measurements back up to the value pre-resistor divider or pre-voltage divider, and then sending those measured values over the serial connection to the computer. And so here we have you can see the board. We have JSD connectors for each of the balance terminals for the battery, where we connect and measure the cell voltages. We have the resistors for the voltage divider, and the board is all conformally coated so that water droplets or dust or other debris that gets on there does not short out the batteries accidentally. And we also have a quick schematic of the voltage dividers themselves. The emergency system is composed of 2 subsystems. The first is on the boat and includes the hardware to control the status light and disconnect the motors. And the second is handheld and allows the user to remotely stop the boat and monitor the connection status with the emergency system that's on the boat. And so safe in all practical failure modes, such as power loss, signal loss, or runtime error on either of the 2 subsystems. And the flowchart to the right describes the behavior of the onboard subsystem. And so you can see it basically is continuously receiving messages from the transmitter indicating whether or not it is in the emergency state. And depending on whether or not it gets it, it will either enter the emergency state or stay in the normal state. And if it fails to receive 3 messages in a row, it can be assumed that a connection has been lost. And so the boat is put safely into the emergency state. So the motors are shut down. And so for the onboard portion of the system, both systems actually use the Adafruit Feather LoRa board. It's a integrated Arduino or Atmel processor with a LoRa radio, and was fabricated in a waterproof enclosure, as can be seen on the lower left. The switches were selected for their water and dust resistance, and importantly, their EN 418 certification, which certifies them as acceptable for emergency stop applications. Similarly, the lights were selected as they meet the SAE Class 1 certification, which allows them to be used in emergency vehicles. And so they're visible at all times during the day and in bright and direct sunlight. We have the two schematics over the left that describe the system. The lower one is of the components inside of this enclosure, and we can see those here. And so the upper one is the components that are located either within the boat or on the boat. So we have like the stop buttons and the motor relays for cutting power. The remote system has the same board, but it has an OLED screen that also displays the connection status in terms of RSSI and the packet drop and success rate. It also displays whether or not it's connected directly in addition to those packet drop and success rate, and whether it's in the stop or normal mode, as well as also displaying the percentages for both the transmitter's battery and the receiver's battery. We first used the TNC as a PWM signal generator when we did our first pool test, and it worked great. And we found that it had enough serial throughput and processor time to handle 2 additional tasks. So GPS and IMU modules from Adafruit were added, and they both stream their data out over the serial line while the motor is receiving control signals, which is receiving control signals to set those PWM values. The protoboard PCB to the right was fabricated to hold all these sensors in place. And it was all put inside a 3D printed enclosure so that the GPS's antenna, which is this gold little piece right here, could be securely mounted. 2 other sensors that we're using in addition to those are the Z stereo camera, which is used to collect image data for object classification and to obtain distance measurements and estimate orientation using comparison of frames. The LiDAR that we have, the RP LiDAR, was purchased by a previous team, and it only scans in one plane. So this is not really practical when scanning out against the horizon, and so we decided to mount it as a push broom configuration. So it's mounted at an angle to the horizon, and it's basically scanning what's immediately in front of the boat, so it can detect any obstacles that the boat may be at risk at colliding with. For our compute, the Raspberry Pi and the TX2 kind of work hand in hand, but the Raspberry Pi is used as the boat's main control computer, and it's where the TNC actually connects to. And so if the TX2 were to fail, the boat could still be driven using the Raspberry Pi. And the TX2 is really only intended for data processing and logging. And so it interfaces with all of the high throughput sensors, such as the Z camera and the LiDAR, so that the data from these sensors does not have to be unnecessarily transmitted over the network. And all of the, really all of the general control operations are just done by the Raspberry Pi. And those 2 are connected using the TP-Link AC1750 router. They're connected with Ethernet through that router, and that router is also how you connect to the boat to control it. So you connect to that network with a laptop, and you can control the boat. We decided to go with ROS to provide the single source of truth, primarily because of its large library of packages and API that make integration and maintenance significantly easier. 3 of the packages that we're using, the first is ROS Serial, which is used by the battery monitor to send cell voltages, and is also used by the TNC to receive motor control signals and send GPS and IMU data. ROS Bridge Server is used to create a WebSocket to gain publish and subscribe access to all of the network's topics in a web app. And ROSBag is used to record and playback sensor data for later analysis, which can be used when collecting data for machine learning. We're using 2 APIs, the RP LiDAR API and the Z API, which allow us to interface with those 2 sensors respectively. And so the human machine interface was developed with ROS Bridge. It's a website that was developed with HTML, CSS, and JavaScript, and it provides real-time control and real-time monitoring of the boat. And I'm gonna just mention it briefly here, but we're gonna come back and look at it at the end with a demo. The motor mounts on the boat needed to be redesigned because the previous orientation or the previous position where they were mounted had holes in the bottom of the boat that were consistently leaking, and we couldn't get them to be patched, and so it just needed to be redesigned. And so it was designed in 2 parts, connected through a dovetail joint so that it could be easily disassembled when transporting the boat, and to also make the parts easier to print. The motor was also located as high as possible in the water, which reduces the torque loss as seen by a boat pitching up when it's accelerating or decelerating. And it was also located as far forward as possible, which decreases the turning radius as the motors are closer to the center of the boat. And these mounts are fabricated with 3D printing. So on to our testing. The battery monitor was calibrated and tested at charge voltages between 3.2 and 4.2 volts. These are like the accepted minimum and maximum charges for a lithium polymer battery. And for these tests, they were first discharged all the way to the bottom range, and then the batteries were measured with a multimeter to gain their actual value, and then plugged into the battery monitor board, and the recorded value was measured. And so the absolute difference after the calibration, the absolute difference is in our test between the battery monitors were then averaged. The maximum of those absolute differences were taken for each of the cells. So for the 6-cell battery, there would have been 6 averages that you were going between. And their values can be seen in this row here. And so the average of all of these is 0.4, and the highest absolute maximum difference that we have is 0.6, and that's within our 0.1 volt requirement that we specified. The emergency system, we were able to test 3 of these criterias. Duration, first, is to test for intermittent errors, and so we ran the transmitter for approximately 4-hour test durations. And we ensured that there were no disconnect events, and we made sure that it was reliably working at 30-minute intervals and able to safely make and break the motor power. The latency is a test to make sure that the time between triggering the emergency switch or the emergency stop and it actually being executed is not too significant. And so we did this using an oscilloscope connected to the output and the input of the emergency systems. And the time that we had specified was 2 seconds, and for both of those, the worst case is 400 milliseconds, and so that's well within what we required. For the latency test, we wanted to, the disconnect, that test that I just described was the latency test, but for the disconnect test, that's just to make sure that whenever the transmitter and the receiver lose connection with one another, that the boat safely enters the emergency state. And so we did that test 10 times for the transmitter, where we just turned off power and made sure that it entered the emergency state. And those 3 were able to be successfully completed. We were not able to complete these test methods because of either limitations as far as how much time can be spent on the project now, because I'm the only one who can be working on it as the boat's in my house, or because we no longer have access to facilities to perform the tests. Here's our schedule. Everything is pretty much buttoned up with the exception of that testing. We might be able to complete a little bit more in the next couple of days before we have to submit everything. But for our budget, basically our highest spending categories were our emergency system and power distribution system. And so the cost in the emergency system is primarily because we selected components that were rated for this emergency stop use case, and those tend to be more expensive as they're designed to be more reliable. In second place, though, is the power distribution system, but we were quite close to our budget and we spent it well. But now on to the demo. And so we'll pull up my screen share. First, change my camera. Change my screen share. All right, you guys see my web browser? All right, cool.
Yes.
So I'm gonna open up this. So this is the human control interface, and while that's still loading up, I'm going to show you quickly the remote emergency stop. And so you can see behind me on the boat, there's a red flashing light, which indicates that it's in the safe state. Motor is disconnected, or power is disconnected from the motors. And so if I were to lift the switch, it switches yellow, indicating that we're now in the manual control mode. And if you were to close it again, it should, go back to red. Similarly, if we press manual here, it changes over to blue, indicating that it's in the autonomous functionality mode, so that now it would be piloted autonomously. The actual functionality of this button could be increased later on, but it's just to show that we can send the control signal, so you could make this so it would do like a specific autonomous course, like the channel navigation course. Below here, we have the live stream from the cameras from both sides of the Z camera. Here we have an orientation and acceleration plot, as well as an animation. So you can see here, if I, let's move this a little closer here. If I move the boat, you can see that reflected in the animation there. So that's in the pitch, that's in the roll. And then lastly, at the bottom, we have the GPS data that's both given in coordinates and then also plotted in a map. But that's it from us, and we'll take any questions. Oh, wait, I lied. There's also the controller. So it's controlled with a, it's the game controller, like an Xbox or a Logitech controller. And so you can see on screen those two plots moving around to indicate the position of those. And so each of these joysticks control a motor independently. So full forward, full backward, turning.
Are the motors currently hooked up, or?
No, no,
Okay.
they can't run out of water. Yeah. If they run out of water, they'll just soak. Yeah.
Okay, all right. So you're just demonstrating there that that your software interface can see the signals from the controller, is that right?
Well, it's verifying that it's actually being published to that topic, because the way that I made this update is so that it does not read the value from the controller and then immediately plot it. It waits until it sends, and then it subscribes back to whatever it just sent. So it makes sure that's actually getting to where it's going. And we verified the PWM signals generated using an oscilloscope connected to the TNC motor board.
Can you talk about that chart right there where you're showing the battery charge? What's that showing us?
So if you hover over it, it gives the individual cell voltages, and so you can see those distributed for each one of them. So for the 4-cell battery there, we have voltages, like for the smallest cell, we have 4.13, 4.2, all the way up.
Okay.
There's nothing connected. So there's 2 3-cell battery connectors, but there's nothing connected to this one. We only have 3 batteries in the boat right now. And so this one's just empty. We just added it in case another team wanted to add another battery on.
Oh, okay. And so the horizontal axis is showing total voltage.
Yes. And so that because they all stack.
Yeah. Cool. I don't want to, does anyone have any questions from the audience? A big audience here. Anybody with some questions?
None for me, but thank you for asking.
Hi, this is Chang Hee-Won. Can I ask you a question about the orientation sensor that you had?
Yes.
Yes, this seems like, so those are degrees, roll your pitch?
Yes.
And if you rotate it, it actually changes. Can you do that?
Yes, I can do that again.
One more time.
So we pitch it. You can see it's plotted there as well. So we roll.
Oh, that's not 400 degrees, is it? Because it seems like that.
No, the way that the website is updating, sometimes it does error out like that. If you look at the actual topic data, I still haven't figured out exactly why it does that.
Oh, really? Okay.
Well, right now it's at 360 degrees, so it overflowed from 0 to 360. So it's barely at the. See if I just tilt it in which direction is that? Z.
So this is.
See, now it goes back to 0.
Is this data from IMU?
Yes, this is data from the IMU. It's at 360 degrees here. So it goes from 0 to 360 when you bring a negative.
When you are using IMU, you have to initialize it first. Then you have to either use accelerometer or gyroscopes, right? Which sensors you actually use to calculate this angle?
No, this IMU, it's one made by Bosch. It actually has a Cortex M0 processor in it, and so they're actually fusing all the data from the from the magnetometers that they have, as well as from the accelerometers and the gyroscope on there to just give you an absolute orientation output.
Oh, so
And so you don't have to do any of that. Yep.
Okay. That's all the question I have. Thank you.
Any other questions from the audience? Can we just talk about maybe, so you have a lot of nice demonstrations here. If assuming the situation was normal, what kind of other experiments would you want to run with this, given where you're at now and where you want to be?
I mean, it would be great to actually put the thing in the water and try to drive it around for an extended period of time. Because like the one thing that Dr. Bai and us were concerned about is the latency for the video. Because ideally when we're training, when a team would be training the model, they want to be using only the data that the sensor or the model would actually have access to when making decisions. And so you wouldn't want to be like training the model by looking at the boat from like just like a normal perspective and driving it around. You want to be looking at what the cameras can see and make your decisions based on that. Otherwise, you're going to be giving it some weird input that it doesn't understand. And so that is what we would like to try to do. You're initially going to go to a park by my house, but it just didn't work out.
Yeah. And then I guess the only other question I was wondering about is, were you able to validate the battery monitoring system, or I guess how do we know that that's reporting the right voltages and things like that?
The battery monitoring system?
Yeah.
I thought we discussed that. Was in here. Battery monitor. Let me change my share.
Maybe you did. I might have just missed it. Oh, you did. That's right. You showed experimental results, right? You had a max difference of 0.04. Okay, now I remember. I'm sorry.
Yep.
Okay. I don't have any other questions. Anyone else in the audience have questions?
How shallow is the boat able to go?
How shallow? I think the lowest point on the boat still is going to be the motors. And so it probably could go, assuming that you're like talking about a pool and not like any debris that's going to get sucked up into the motors, like you would get like a pond or something. I think you could comfortably drive it around in as little as a foot of water, as long as you're not too crazy on the acceleration, causing it to pitch up.
Are you worried at all that like murky water would interfere with the boat's ability to navigate well?
Not really. I mean, we're designing for the competition, and so the competition is at like a pond. It's like at a nice pond, and we've seen pictures of it. It's like things in the water that we're not expecting are not really something that we have to be too concerned about. And competition staff are also in the water, so they're going to be clearing out any other debris that, like any sticks or anything else that you might be running into. And so it's not really something that we have to consider.
All right. Well done. Thanks everyone for your time, and you guys take it easy. Stay safe today, and I'll see you all later. All right.
Thank you.
Thank you.
All right. Thank you very much, team.
Very
Talk to
nice
you
job.
later.
Thank you, Dr. Bai.
Great job, Byron.
Thank you.
That was Peter, by the way.
Thank you, Peter.